Now let's talk about functions in R4. Whoa! Here's an example. W is a function of x, y, and z. We input a point x, y, z, and we output a value w. So in this case, f is a function that maps from R3 to R1. We input x, y, z, and we output a value of w. So what we could do here, I'm going to draw a box in 3D. I'll draw it real brief here. So this is positive x, positive y, positive z. And what happens is we input values inside this box. These are all 3D points. And for each point that I input, it outputs a value onto, let's say, the W scale. Here's 0 through whatever. And so perhaps this point's here, and if I input this point here, perhaps it outpoints here. Now we can't visualize a graph of W because it goes into fourth dimensional space. That's why we call this in R4, because the graph is in R4, and then that can't be visualized. I would like to give some contextual meaning to this R4 business. So picture this box again, and suppose this box represents a room. It could be a room filled with air, it could be a room filled with water, and at each point inside the box, it has a temperature. So these points belong to R3, three-dimensional space, but at each point, it gives us a temperature. So W could represent the temperature at point X, Y, Z. Perhaps this box represented a solid, and at each point in the solid there was a different density, in which case here W could represent the density at point X, Y, Z. And remember, we can't picture a graph of the temperature. We can't picture a graph of the density because it goes out to R4. Now, there are ways that we get a visual sense of it. In an earlier lesson, we talked about functions that mapped from R2 to R1. Those are functions that have a graph in R3 and then have a level curve in R2. So an example would be any function of the form z equals a function of x and y. And if you recall, the level curve gave us constant values for z, and then that mapped in R2. So what we're going to talk about now are functions of R3 mapping to R1. That graph is in R4. Now I say graph loosely because there is no graph, and instead of a level curve, we're actually going to have a level surface. And that level surface is going to be a three-dimensional shape. So that's pretty cool. Again, those examples are W is a function of X, Y, and Z. Let's define a level surface. A level surface of the function W equals f of x, y, z is the equation f of x, y, z equals k for some constant k. An example of that might be f of x, y, z equals 10. This is a level surface. It doesn't give us the entire function. It just gives us what the function looks like when the output is 10. As a visual, picture a sphere inside this 3D square that we've drawn, and that might be f of x, y, z equals 3. So this hollow sphere would say every point on this hollow sphere had a temperature of 3. But if we move off the sphere, still inside the box but outside the sphere, well, this function here would not equal 3. So a level surface that passed through this point would be different than the sphere. Perhaps it's a concentric sphere and it would go around like this. but that's what a level surface does. It tells you the value of the function for every point on a surface. But if I combine all the level surfaces, well, then I would fill in this cube, and it would be a dense solid color because the function would be continuous. Now a note on gradients. Functions that went R2 to R1, well, we talked about that gradient, which we labeled del f, which was par f, par x, comma, par f, par y. Now a gradient is just an extension of that. Del f, which is del f of x, y, z, for scalar function f of x, y, z, is just going to be par f, par x, par f, par y, par f, par z, and you see that that points in three-dimensional space. So I'm going to come over to my sphere that I have drawn here, and suppose at this point here I wanted to look at the gradient. That gradient is going to point away from the sphere. It's going to be orthogonal to the level surface. So if you pictured a tangent plane to the level surface, the gradient is going to be orthogonal to that. That's an important property. The gradient is always orthogonal to the level surface. And that tells us that del f points in the direction of quickest increase. And of course, the magnitude of del f is the maximum rate of increase. Let's take a look at this example, w equals x squared minus y squared plus z squared. If I were to graph that, what shape would it make? No shape. This would be a graph in R4. This doesn't have a shape. This function, w, is a function of x, y, and z. It maps from R3 to R1. The domain of this function, w, well, there's no restrictions. I can plug any x, y, z combination in there, so there's no restriction. So the domain is going to be all points x, y, z, such that x, y, z belongs to all of R3, of all three-dimensional space. So every point in three-dimensional space is a point of the domain. Let's go ahead and give some context to this. W is going to be the temperature, degrees Fahrenheit, at points x, y, z. Let's say that x, y, and z are in meters. Let's take a look at some level surfaces. So let's let w equal 0 and figure out what that surface looks like. So now we're going to have 0 equals x squared minus y squared plus z squared. Now, since this is a level surface, it has a three-dimensional shape, and you should be able to look at this and determine what three-dimensional shape this is. It is a cone opening in y. How about the level surface w equals 4? Well, then we're going to have 4 equals x squared minus y squared plus z squared. That level surface has a shape that you should recognize. What is it? What is it? It's a hyperboloid of one sheet opening in y. For w equals -4, we get -4 equals. And if I just multiply out a negative here, I get negative x squared plus y squared minus z squared. And you should be able to tell that shape, which is a hyperboloid of two sheets that also opens in y. Let's take a look at some of these level surfaces graphed together. First, I put a yellow box around the cone, so let's draw that first. So there we have the cone. Next, we have the hyperboloid of one sheet, which resembles like a nuclear tower. And finally, I have the hyperboloid of two sheets, which I've drawn in red. So on the hyperboloid of two sheets, if we're talking about temperature, the temperature is always equal to -4 along the hyperboloid of two sheets. Along the hyperboloid of one sheet, the temperature is always +4, and along the cone, the temperature is always 0. You put all the level curves together, you get the entire R3 region. If it's a room, you get the entire room. And imagine in a room you had temperatures that had along a cone were 0, along the hyperboloid of one sheet were a different temperature. If you add up all the level surfaces, you get the entire room. Now for gradients and directional derivative. So the gradient of our function, if we're keeping with the same function, the gradient will be 2x negative 2y comma 2z will give us that vector. At the input point negative 1, 1, negative 2, then f would be, let's just compute this real quick. So f would be negative 1 squared minus 1 squared plus a negative 2 squared, and that would come out to be 4. So at that point, w is equal to 4, in which case we get the hyperboloid of one sheet as our level surface. And now our gradient at that point is going to be negative 2, negative 2, negative 4. It's going to be a little hard to visualize this on the graph, but this gradient is orthogonal to that hyperboloid of one sheet. And it gets harder and harder to visualize these things as the dimensions increase. So this means now that this gradient at point P is the direction of quickest increase, in this case temperature. And the maximum increase in temperature is 2 radical 6 degrees Fahrenheit per meter. Now the directional derivative works the same way as we did earlier. It is the projection of del f onto the vector v. So if we're going to move in the direction from point P to point Q, we want the vector PQ, which is just the difference of corresponding components, which is 5, 1, negative 1. So that's our vector v. So our directional derivative is the component of del f onto vector v, del f dot v over the magnitude of vector v. So we have del f at negative 2, negative 2, negative 4, dot 5, 1, negative 1, all over the magnitude of that, which is the square root of 25 plus 1 plus 1. And in the end, this comes out to be negative 10, negative 2 plus 4. I might as well do the dot product. Okay, over the square root of 27. So that comes out to be negative 8 over the square root of 27 degrees Fahrenheit per meter if we move in the direction from point P to point Q. I hope you find this example as exciting as I did. The example itself is not that exciting, but the theory is pretty awesome. In this question, they want an equation of a tangent plane to this surface at this point. Okay, now it turns out that this surface is an elliptical cone. We'll just call it a cone. So we want an equation of a tangent plane to the cone at the given point. This is not in R3. In fact, this is not even a function. Now, what we're going to do to this, in order to find an equation of a tangent to this surface, we're going to need a normal to this surface. So what we're going to do is we're going to pretend that this cone was just one of many level surfaces to some greater function w. So let's let w equal x squared plus 3y squared minus z squared. Nowhere in the problem does it say that. We made that up. We induced this fourth dimensional function so that if we let w equal 0, then we have this elliptical cone as a level surface. And the gradient of this induced fourth dimensional function w will give us the direction of a vector orthogonal to the surface. And we'll need del W at our point 1, 1, 2, and that will yield the vector 2, 6, negative 4. So now we have a normal vector to the surface at the point 1, 1, 2, and we have the point 1, 1, 2, and that's all we need to come up with the equation of a tangent plane. So we have 2x minus 1 plus 6 times y minus 1 minus 4 times z minus 2 equals 0, recalling the equation of a plane. And in the end, if we simplify this, it's x plus 3y minus 2z equals 0. That's pretty cool, right?